Tonight we're going to look at Coulomb's law in two dimensions, so not just the distance being in a straight line, and with multiple charges. So Coulomb's law is going to get more complicated tonight. Here's a problem. I'm just going to work through this example so you can see what's going on. You'll need graph paper, so if you need to grab your notebook that I told you to get that has the graph paper in it, go grab that, or find some graph paper, you need that. Here we go. A positive 1 microcoulomb charge is located at the origin. So I need to set up a coordinate system that has an origin. I'm just going to draw an xy axis on here. There's my xy axis. And let's call this point right here the origin. So that's the origin, usually called O. And at the origin, we have put Q1, which is a positive 1 microcoulomb charge. Now, I gave that a number just to make it easier. There's going to be a bunch of charges on here, so that will be Q1. A second charge of negative 2 microcoulombs is placed at the coordinates 1 millimeter, 0. Well, if I'm just doing this with like 1, and I see down here later another coordinate that's just 1, I'm going to say that every 5 boxes is 1 millimeter, just so things can be spaced out. 1, 2, 3, 4, 5. So I'm going to put my second charge, Q2, is right here, and it is a negative 2 microcoulomb charge. And just so I don't forget, this point here is 1 millimeter, 0. Now lets me know that those 5 boxes are still just 1 millimeter. A third charge, starting over, of 3 microcoulombs is placed at coordinates 0, negative 1. So 0, 1, 2, 3, 4, 5. That's the coordinates 0, negative 1 millimeters. And that charge there is 3 microcoulombs. And since it doesn't give me a sign, it's going to be positive. So if there's not a negative, it's positive. So that's positive 3 microcoulombs. What is the magnitude and direction, this is missing some words, of the force on the charge at the origin? So I want to know how much force Q1 gets. It will get a force from each charge. And you simply figure out the force from each one and then add them up using vector addition. So forces are vectors. You can't just add the numbers. You have to add them using vector addition. So let's find the force from each one. Let's look at Q1 and Q2. Q1 is positive and Q2 is negative. So they will attract. And since we're worried about Q1, we know that Q1 will be attracted to Q2. It is also true that Q2 is attracted to Q1, but we're not concerned about that right now. We're looking at Q1, the charge at the origin. This force vector here, I will label F, Q1, Q2. Let me talk about what that means, because this is a naming convention in physics. What we do is we put the charge getting the force first, the charge giving the force second. So you would read this, the force on Q1 from Q2. And actually, by Newton's third law, the other one would have to be the same, equal and opposite forces. So the force on Q2 from Q1 would be the same force. But we label it this way to let each other know what we're talking about. So I'm talking about the force on Q1 from Q2. And we can figure out the amount of that force later. Second part. Q3 is a positive charge, and since Q1 is also positive, Q3 will repel Q1, and we will get a force pushing Q1 away from Q3. And these charges do push in straight lines, so it would push in a straight line from Q3 to Q1. So this red vector would be the force on Q1 from Q3. And now, when we eventually figure out the amount of that force, we're going to need to know the direction, and we can use vector addition to do this. So I'm going to figure out just the direction right now. Let's put together, this is FQ1, Q2, just redrawing that. And then vector addition says I pick up the second vector, put its tail at the tip of the first. This is F, Q1, Q3, force from Q1 on Q3. force on Q1 from Q3. The resultant vector would then be here. So this is the resultant vector. So Q1 is currently getting pushed up and to the right. That's the direction of its force. Okay, so I've done all that, and now I've got its direction. Check. I still need to know how much force. So let's work on that part next. Okay, so I've minimized all that stuff, just so we can keep it around. Now I need to know the amount of charge from each one. So first, let's figure out the amount of charge on Q1 from Q2. F Q1, Q2. Now this is simply Coulomb's law. K, Q1, Q2 over the distance between them squared. All right. K is just 9 times 10 to the 9th Newton meters squared per Coulomb squared. Charge 1 is 1 microcoulomb, or 1 times 10 to the negative 6 coulombs. Charge 2 is negative 2 microcoulombs, or times 10 to the negative 6 coulombs. And the distance between them is 1 millimeter, which would be 1 times 10 to the negative 3 meters. It's because millimeter, you move 3 places, so that makes it negative 3. All right, and it's the distance between them squared. So now I can easily find force Q1 on Q2. And I find that the force on Q1 from Q2 is 18,000 newtons. I'm going to check me, that seems high. But for the sake of time, assume I'm right. Now let's figure out force on Q1 from Q3. F Q1, Q3. Same process. K, Q1, Q2, distance between them squared. 9 times 10 to the 9th Newton meters squared per Coulomb squared. Charge 1 is still 1 times 10 to the negative 6 coulombs. And charge 2, different this time, is 3 times 10 to the negative 6 coulombs. Noticing here that force Q1, Q2 is technically negative. However, that's a worry about direction, and we'll include we've already done direction up here. So once I get the magnitudes, the direction's already taken care of with my resultant vector. So remember, with vectors, plus and negative is an indicator of direction, and we've already handled the direction. Distance between these, also 1 times 10 to the negative 3 meters squared. Now notice that distance is easy because they're in a straight line from each other, both of them. If they were like one of the charges over here, you'd have to use the Pythagorean theorem to figure out that actual distance. Okay, so now F Q1, Q3, and force on Q1 from Q3 is 27,000 newtons. If you are thinking to yourself, okay, we add them and we're done. No, no, no. Notice they make a triangle. So up here, when we drew the tip to tail and got the resultant vector from vector addition, notice that shape is a triangle. And so we're going to have to use the Pythagorean theorem. So F Q1, Q3, that vector has a length of 27,000 newtons. F Q1, Q2, that vector has a length of 18,000 newtons. So we have to use the Pythagorean theorem to add them because they're two sides of a right triangle. Okay, so now that we've found all that, all that's left is to add them using the Pythagorean theorem, which says c squared equals a squared plus b squared. And I've color-coded them like the vectors I did above. Okay, so we're looking for the resultant vector, which is c. And we have the lengths of the two side vectors, which we decided were 18,000 newtons and 27,000 newtons. So let's add these together using the Pythagorean theorem. So c squared equals 18,000 newtons squared plus 27,000 newtons squared. And then once I have that, I'll take the square root to get the final answer. And I got that C is 32,000 about 400 newtons. So that is the magnitude of the resultant vector, the force on Q1. So the force that Q1 is experiencing from all the charges is 32,400 newtons, and the direction up and to the right, so that away. So that is our force vector, and that answers that question. This was a lot. I'm going to encourage you, if you are confused, go back and watch again, because you got to know how to do this for the lab tomorrow.